Section 15.6, finding surface area. So you've got this three-dimensional function and it's over some region. So this is in the xy plane. And for some reason they call it D instead of R, but it's still a region in the xy plane. And the idea is the function is above it. So it's up here in three-dimensional space. And you take this region, project that up to the function, and then what's the surface area that it would have if it was glued to the function. So the surface area is, you do a double integral over the region D, and it's going to be 1 plus, you take the derivative with respect to x and you square it. You take the derivative with respect to y and you square it. And then set up dy or dx, and that's how you find surface area. So if you remember Math 3b, when you do that integral, well, as a single integral in Math 3b, then that's finding the arc length. Well, arc length is very similar to surface area, except it's got an added dimension. So for example number 1, find the surface area of a sphere. And this sphere is going to have radius 5. So there's actually two ways that we could do this. One is using 8th grade geometry. The surface area for a sphere, the formula is 4 pi r squared. So that will be 4 pi 5 squared. That's a 25 times 4. That means that the answer is 100 pi. Or we could do it the fun way and use third semester calculus and come up with the same answer. So now we'll do that. So for example, number 1, a sphere is x squared plus y squared plus z squared is equal to the radius squared. And the direction said you need to solve for z. So solve for z. So you need to subtract the x squared and the y squared and then take the square root. So z is going to equal the square root of a 25 minus x squared minus y squared. And then we need the derivative with respect to x. So since this is a square root function, its derivative is 1 over 2 times that square root. And then don't forget the chain rule, so the derivative of the inside is going to be negative 2x. And then we could have these little 2's cancel. Then when you take the derivative with respect to y, it's going to look exactly the same, except this part's going to say negative 2y, and then the 2's will cancel. See, isn't this already more fun than just the 8th grade way to do it? All right, now we need to set up a double integral. It's going to be the square root of 1 plus, and then each one of these needs to be squared. So that derivative gets squared and this derivative gets squared. Then my square root needs to be longer, and then dx and dy, or dy and dx. Now we need limits. So basically what you could do is, you've got this whole sphere, you could then cut it in half and find the surface area of half of it. And then double that answer. So I'm just going to integrate over half of it. So if the sphere had been sitting right here, then I cut it in half with the paper, and then I would just have the top half of it. And where the paper cut it, that would make a circle of radius 5. So this function right here is x squared plus y squared equals 25. Or if you solve for y is equal to, so subtract x squared and take the square root, so plus or minus the square root of 25 minus x squared. So I just solved for y, so actually I would need to do dy dx. Although I have a feeling we're going to change to polar anyway. But the y would go from the negative square root to the positive square root. Negative the square root of 25 minus x squared to positive square root 25 minus x squared. And then for x, it would go from negative 5 to positive 5. Whew, that's a beauty. All right, now let's change it to polar. Well, maybe I should first do a little bit of algebra, because if I square this, that's going to be x squared plus y squared. And x squared plus y squared equals r squared. I think I should do a little more algebra first. So when you square these two, the denominators, the radicals are going to be gone, and the denominators are the same, so those two can be added together. So that's going to be 25 minus x squared minus y squared. And then when you square the numerators, there's going to be x squared plus y squared. And then there's going to be this 1, and then dy dx. And right now I'm not going to bother putting the limits because I know I'm going to change to polar anyway. So in polar form, this is r squared. And if you factor out the negative, then this is going to say 25 minus r squared. So inside the radical, there's going to be 1 plus, and then this is r squared over 25 minus r squared. And then we're changing to polar, so then it's r dr d theta. And then r means the radius. So the radius would go from 0, and then it would go out to 5. And then as far as the angle, to create this whole circle, you need to go from 0 to 2 pi. All right. Then the next thing we should do is change this so that we can add these two fractions together. So change this to be 25 minus r squared over 25 minus r squared. So then it's going to be 2 times so change this one to be 25 minus r squared over 25 minus r squared plus an r squared over 25 minus r squared, and then r dr d theta. And then that actually works out pretty nice, because when you add these fractions together, those little r squares, that one's negative and that one's positive, so they're going to cancel each other out. So then it would be the 2 integral 0 to 2 pi. And then when they cancel each other out, it's just going to leave a 25. And the square root of 25 is 5. and then the denominator would still have the square root of 25 minus r squared. And then there's the r dr d theta. And then with this, we could use u substitution. So let u equal 25 minus r squared. Du is negative 2r dr. And then we don't need the negative 2, so multiply both sides by negative half. And so I'm just going to work on this part right here over on this side, and then we'll continue with the whole problem down here. So just to finish this u substitution right here. So then that would be integrate. It would have a 5, and then on the bottom that's going to become the square root of u. And then the r dr, so the r dr becomes du times a negative 1/2. So du times a negative 1/2. And then you could rewrite this as u to the negative 1/2. And then the antiderivative is going to be u to the 1/2 divided by 1/2. And when you invert and multiply, it's going to cancel this 2. So it's going to leave negative 5 and the square root of u. So now continuing this down here, the 2 would be on the outside. We're still going to need to integrate from 0 to 2 pi in a moment. And then the 2 and that 2 canceled out, but there's still a negative 5. So I could just move that negative 5 out here. And then this is going to be the square root of u, so that's going to be the square root of 25 minus r squared. That's being evaluated from 0 to 5. And then the only thing that's missing is d theta. So when you substitute a 5, this is going to be 25 minus 25, so that's 0. Minus, when you substitute a 0, that's just going to be the square root of 25, so that's a 5. And then there's still this. And then this is a negative 10. And then this is going to be negative 5, which that negative 5 you could factor it out. That makes this a positive 50. The antiderivative of d theta is just theta. And then theta gets evaluated from 0 to 2 pi. So finally the answer is 50 times 2 pi minus 0. Or in other words, the answer is 100 pi. Which is exactly what we were supposed to get. So you could do it 8th grade way, done in 2 steps, or the more fun way, the calculus. Woot woot! Thanks, calculus. And for example number 2, finding surface area. So here's our function. It's already been solved for z, so that's good. Notice that it's got a little graphing calculator symbol right here. So when you set up these integrals, and because there's a square root, they're often extremely difficult to integrate, so sometimes you need to use technology. But first we need to set up the integral properly before we go to the technology to integrate it. So this is the region, and then this is a parabola. Y equals 4 means cut it off right here. And then if y is equal to 4, it must be that this was a negative 2 and this is a positive 2 on the x-axis. Y equals 0 just means the x-axis. So this is the region that's being talked about. Now set up the integral. So we need the derivative with respect to x. So that will just be 8x. And we need the derivative with respect to y. So that will be just 2y. And then set up the double integral. And then it's the square root of 1 plus this derivative gets squared plus this derivative gets squared. And over here, you can put dx dy or dy dx, and I should have put dy first because this says what y equals, and so I want to go with that. So good thing I can just write over it, make a nice pretty picture. There we go. So then y goes from what to what? So the y has to go from the smallest value up to the biggest value. So the smallest value is the parabola. So that's when y equals x squared. And then the biggest y gets is 4. And then as far as x's, they range from -2 to 2. Now because this integral has 2 variables, I can't use one of these. So we need to use a computer. So now to finish up number 2, we need a double integral calculator. So of course, just Google that. And my favorite is Wolfram Alpha. So I'm going to go to Wolfram Alpha. And then you need to tell it what the function is. And ours is the square root. And for that, I'm going to use a 1/2 power. So then it was 1 plus 64x raised to the second power plus 4y raised to the second power, and all of that is raised to the 1/2 power. And then you get a choice of dy dx or dx dy, so ours is dy dx. X goes from, I don't know why they put x first, but anyway, x goes from -2 to 2, and then y goes from x is squared to 4. And then I'm just looking to make sure that I typed it in right. It looks good, so there we go. And there's the answer, 87.0329. And for example number 3, finding the area of this function that's inside this cylinder. So the way that I visualize this one, this is a right circular cylinder, radius of 1. So the function of cosine is doing something like this, because it's a cosine function, so it must be wavy like that. And then you take a cylinder like this, like a cookie cutter, and then you just cut it out. And then what would be the area of the thing inside there? That's what we're going for. All right, first of all, it's already solved for z. That's good. And now we need the derivative with respect to x. So the derivative of cosine is negative sine, then it's x squared plus y squared in the parentheses. And then do the chain rule. The derivative of the inside is going to be a 2x. Then the derivative with respect to y is going to be very similar. Negative sine of x squared plus y squared. Then do the chain rule. The derivative of the inside is a 2y. And then set up the double integral. It's going to be the square root of, yeah, I'm not even kidding, 1 plus, and then this one gets squared. So if this gets squared, that means it's going to be sine squared, and that's going to be 4x squared. You get a square, and you get a square, and you get a square. And then plus this one squared. So that's going to be 4y squared and sine squared. So plus 4y squared and sine squared. Oh, see, you thought I was kidding when I made the radical that long, but nope, we needed it. And then dx dy or dy dx. So there's an x squared plus y squared right here. There's also an x squared and a y squared with a plus right there. So that's telling me we should probably change to polar. Well, one thing I could do first is factor it, because these two both have sine squared, and they both also have 4. So it's going to be 1 plus, so we could factor out the 4. We could also factor out the sine squared. And then what remains? So this is the only thing remaining from this term, and this is the only thing remaining. So it's x squared plus y squared. And then it's a good time to change to polar. So it's going to be the square root of, so all of this stays, this right here becomes r squared. So it's going to be 1 plus 4 sine squared r squared. And then this is another r squared. And all of that is inside the radical. And then because we changed to polar, this is going to be r dr d theta. And now this is a circle of radius 1. So that means that r is going to range from 0 to 1. And then in order to get the whole circle, the theta will have to range from 0 to 2 pi. Now, the last one, in here there was more than one variable. But if you look at this part, that integral right there only has one variable. So that means I could use and now I can use the graphing calculator to integrate this. So it's going to be the square root of 1 plus 4 sine x squared, and then the sine needs to be squared, and then there's times another x squared, then go outside of the radical, and then multiply with another x. And then take a look at the graph. Although what the graph looks like doesn't matter, but I just need it to graph it so that I can then ask it to integrate. And then number 7, integrate from 0 to 1. And that is a 0.654. So this integral becomes a 0.654, and then we just need to integrate the d theta, which becomes theta, evaluated from 0 to 2 pi. That gives us a 2 pi times the 0.654, so the final answer, 4.109.